Hello, everybody. Welcome to our last major topic in VPython for Physics 1. This is going to be about rotational motion. This is where a lot of the stuff we've worked on so far really comes and makes a lot of real-world sense, because this is where we finally start to work with solid big objects, not just point particles or atoms floating around anymore. Basically, the goal of this section of a Physics 1 course is to talk about what happens when you have a big solid object like this rotating around an axis. So the example I want you to keep in mind here is a cylinder or a disc or a coin or something that's got a nice round extended shape that is rotating around an axis. So the dashed line here represents the axis. That's the line around which it is spinning. So if you think of it like a top, this is the line that goes through the top. And then we're drawing a little red circle here to represent what direction the thing is rotating in. So we need to define some physical quantities to describe this rotation. One of the most important things to describe about this is the rotational velocity. You'll sometimes see this called angular velocity. I believe those terms are pretty much interchangeable. For this, we use the symbol omega. So omega is going to be a measure of how fast the thing is rotating, right? So how fast it is spinning around. In order to do that, I need to think about, well, what is it actually doing when it's moving? Because it's not going from one point to another, right? The cylinder is not necessarily going from this location over to this location. It's really about the whole object turning around. So it's about the thing going through an angle. So really the way to think about this rotational velocity is like a delta theta over delta t. Now that's supposed to look familiar. You're supposed to, in your mind, compare this to regular velocity or linear velocity, delta x over delta t, or if we're going in 3 dimensions, delta r over delta t. Hey, speaking of dimensions, this thing should have some kind of direction to it, right? Because depending on what direction I point the axis of rotation, this thing could rotate differently, right? It could rotate around like this. On the other hand, it could rotate end over end like this, a little bit more awkwardly, like if you're flipping a coin. And so we need to be able to encode direction in this, which means we need this thing to be a vector. But it's not really clear how I turn this rotating circle thing into a vector, right? Because this is not a vector. A vector is a thing that has a magnitude and a direction, but this thing's direction is clockwise or counterclockwise. How do we encode that? What we do is say the direction is given by the right-hand rule. What you do with this, you take the fingers of your right hand, you curl them around in the direction the thing is rotating, and your thumb ends up pointing in the direction of the vector. So we would say that this thing has a rotational velocity vector that is pointing up in this case, because if I take the fingers of my right hand, curl them around this way, my thumb is pointing upward. On the other hand, if it were rotating the other direction, if it were rotating, let's see, so that is counterclockwise. If it were rotating clockwise, the fingers of my right hand would go the other direction. They would be pointing down. And so omega, the vector, encodes two things. It encodes a magnitude of how much angle the thing passes through over how much time, plus, and I'm putting plus in quotation marks here because you're not really adding, it's just saying we're combining these two. It has a direction from the right-hand rule. So we have a magnitude of delta theta over delta t and a direction given by the right-hand rule. And this is like the most basic thing in rotational motion, but it's also one of the most important because this is the thing we're watching. This is the rotation that we are watching. Okay, so let's go back in time to when we first learned about how rotational when we first learned about how linear velocity changes. We had to define a linear momentum as mass times velocity, and we learned that the change in a momentum is going to equal the net force acting on an object times delta t. Well, it turns out we need to do something similar for rotational motion. We need to come up with, instead of a linear momentum, we need a rotational momentum, or an angular momentum is the more proper term. And we also need an equation to tell us how angular momentum changes. So first, let's define what angular momentum is. We need an analog for mass and an analog for velocity. Well, we already know what the analog for velocity is. It's going to be this rotational velocity, omega. But I now need to know what the rotational analog of mass is. And this is something called the moment of inertia. We use I for this. This is moment of inertia. This thing is a quantity that you look up. And I'm not saying that to be snide. I'm saying that because nobody walks around with every single moment of inertia saved in their heads. This is always something you look up. The moment of inertia is usually going to look like some number times the object's mass times its size squared. So this r over here is usually going to be the radius of the object that's rotating. It might be something else, right? If you're talking about a rectangle that's rotating about its corner, it's actually going to be this distance squared plus this distance squared, because you need this distance going this way. So you're doing a little bit of the Pythagorean theorem there. So it's always going to be some number times the object's mass, the entire mass, times r squared. And the way you get this number, honestly, is through some calculus that you do a couple times in your life as a physics person, and you never do it again. You just go and look at it at a table. We're also going to see how to do this with a computer in just a minute. And so instead of mass, we talk about I. So I includes the mass, but it also includes where that mass is distributed. So the way you can imagine this, if all of the mass were on the outside, right? If you had an empty ring, right? So all of the mass is here on the outside. There is no mass in the middle. You would have an empty ring. You would have the biggest moment of inertia you can possibly have. You would have I equals mr squared. Mass times the radius squared is what you would end up with. Because that's the biggest it can possibly be. That number out in front of it cannot be bigger than 1. On the other hand, if you go and fill that mass in, let's say you make it not a ring, but now a disk, then what you actually end up with is an I of 1/2 mr squared, because not all of the mass is on the outside. Some of the mass is on the very inside, and the rest of the mass is, somewhere in the middle there. And so really you end up with a different I for every single shape. So I for a ring is mr squared. I for a disk is 1/2 mr squared. Again, these are not things you memorize. These are things you go and look up and use in the problem, and then go and get on with your life. These are not things you are ever expected to memorize. Okay, so here's our rotational analog of angular momentum. We need the moment of inertia, some number times mr squared times omega. And then we need to know how angular momentum changes. Well, we need the rotational analog for force is going to be something called torque. So this is going to be the net torque times delta t. And so we end up with the net torque times delta t. Really cool. Time is time, fortunately. There is no such thing as rotational time. It's always the same thing. Torque, you might have heard colloquially on like pickup truck commercials or something. Torque is somewhat straightforward. It involves the force, but we have to take a cross product of that force with where the force is acting. So for example, if I push at this disk with a force here on the outside, the r vector is going to be basically the radius going out to that point. So I would take this vector, cross product with this vector. So I know that's a lot of new information. What we're going to do in the next episode is take a look at how we put all of this into an animation code to see how we can actually make a solid object rotate in VPython.